Okay, let us start from where we were discussing in the previous class. The summary of previous class is that we said that there are some mathematical relationships in terms of a line, a straight line, where we have an equation something like this. This is the equation of a line, and sometimes in real data sets we have the points, not the line, and the points all are not exactly on the line. So we have to deal with equations such as this one, where apart from the line there is plus minus some error. We took a few examples of some relationship between two variables. And by the way, these are one-sided relationships, not the two-sided relationships. Sometimes there are two-sided, sometimes there are one-sided relationships. For example, this example of vending machine. Here we are saying that the time to fill the vending machine is dependent upon the number of cases. It's not the other way. If the engineer is taking too long to fill the machine, that doesn't mean that the number of cases will increase.
Can I take my shot on fun?
Yes, sure. So sometimes there are one-way relationships, sometimes there are two-way relationships. So your job is not to decide the direction of the relationship. It's the expert of the variables who will decide the direction of the relationship. Your job as the expert of regression is to look at the statistical part, look at the analysis part. We started with making a number of assumptions. The first assumption we made was that x's are fixed. We assume that the values of x, they are fixed. The second assumption we made was that the sum of errors, and this is a reasonable assumption, that the sum of errors is 0. That means if you draw a good line, the property of that good line should be that the line must follow is that some of the errors should be positive, some of the errors should be negative. Because look, if these are the points, look here, and I fit a line something like this. Is this line representing the points? What's wrong with the line? All the errors are negative. So the mean of the errors is not 0, which means that this is not a representative line. So the line should be representative of the points, and for that, one of the properties, not all of them, I can fit a line that such that the errors are, the sum of the errors are 0. This blue line, if you look at the blue line, half of the errors are negative, half of the errors are positive, still the sum will be somehow 0. So the mean will be 0. So the only property, it's not the only property that the mean of the errors should be 0. There are other properties, but this is one of the properties, ideal properties of the line, that the sum of the errors should be 0, sum or the mean, because mean is nothing but the sum divided by the number. Yes.
Why do you assume x is fixed?
We assume x is fixed so that mathematically when we proceed, the derivation becomes easy. And then at the end of everything, I will let go of this assumption and I will show you that the results are not changed. Even if x's are random, the derivation will be a little complicated, but the final results will be same. So we start with the easier case. Now we were discussing, there was a point where we were discussing that we have two variables, y and x. X's are fixed. There are some specific levels of x, right? At each level, we said that there was a distribution of y, a subpopulation. So when x is x1, there are a number of values of y. And we call it a subpopulation number 1. This is a whole population. This is a whole distribution of y when x is x1. We said when x is x2, there is again a population of y, a complete distribution of y. The distribution of y is assumed to be changing when x is changing. And the only thing that is changing in the distribution of y, we said, is the mean. The variance is not changing. As you go along, the values of x, we are assuming, again, this is an assumption, we are assuming that the distribution of y is changing, but only with respect to the mean. Mean here is this much. If you go along, mean increases. If you go along, mean increases. So in this specific example, the mean of x is increasing as you go along right on the x-axis. So that means if anything in the distribution is changing, the distribution is changing. But we are assuming that the variance of the distribution is not changing. Now, when you take a sample, here this red line, if you connect the means of all these distributions, you will get the red line. The first subpopulation, take the mean of it. The second subpopulation, take the mean of it. The mean of first subpopulation is this one. The mean of second subpopulation is this one. The mean of third subpopulation is this one, and so on. We are assuming that these means, they fall all along the line. That means the relationship between y and x is linear, strictly linear. We start with the linear relationships. Now, if you join these points, you get a line that is red line. Now, this red line, if I take you back to the basic statistics course, do we ever know the population? No. We never know. So this red line is unknown. We never know the population, which means this red line is an unknown parameter. It is like mu, the mean of the population. If you look at this in a simple way, you have a population. For the population, you have a mean, which is unknown. You want to estimate that. What do? You take a sample, and from the sample, you calculate x bar. And you say that this is an estimate of mu, right? Now here, this is a bivariate case, a little complicated case, but the spirit is same. This red line is an unknown parameter. This is an unknown quantity, and you're looking for it. So what you do is, you will take a sample on the bivariate y and axis. You will estimate this very line, and the estimated line may be something like this, or maybe this, but it will be representative as long as your sample is representative sample. We expect what? We expect x bar to be somewhere close to mu, right? So the line you estimate will also be somewhere close to this red line. This red line you will never know. You will never know the red line. So we are looking for an estimate of this red line. This is the whole story of the course. Any question? Now, when you talk about a line, the line depends upon what? Two quantities. The line depends upon two quantities, intercept and slope. If I say I want a line, that means I need the slope and the intercept of that line. If I have those two, I will have the line. So this means that this is a kind of population regression model. True? And you're looking for an estimate of this model, in which you need the estimates of these two quantities. And once you have the estimated model, the final estimated regression line will look like this. you plug in beta naught hat and beta 1 hat instead of beta naught and beta 1 respectively, and the resulting y will be y hat. So this is what you're looking for. The whole story is to what? Is to do the estimation.
The line estimation or
The line, estimation of the line. Now there are several methods in statistics to do the estimation. Several methods. The most commonly used method is method of maximum likelihood. There is ordinary least square methods. There is method of moments. There are several methods to go along. All of the methods, they have their own advantages, they have their own disadvantages. The one we are going to use in this course to estimate these two quantities, and by the way, in this line, there is another third hidden parameter, which I will talk about later. Currently, you see only two parameters in this one, hidden, not the hidden, apparently there is beta naught and beta 1, two unknown quantities, but there is another third hidden unknown quantity. I will talk about that one later. For now, the objective is to estimate these two quantities. Now, to estimate these two quantities, I go back and revise what I'm assuming. One more time. I'm assuming the axis to be fixed. I'm assuming that the expected value of epsilon is 0. I'm assuming that the variance of epsilon is fixed, denoted by a quantity called sigma square. And I'm assuming that epsilons follow a normal distribution. Yes. I did. Let me confirm. Yes. Yes.
Is it a variance or it's just a symbol?
It's a notation for the variance. Sigma square is the notation for the variance.
Yeah, okay, but the variance of the E is constant.
Is constant, yes. Is constant. The fact that I'm calling it constant is because I'm not putting an I here in the subscript. Right? If it is not constant, I will put an I in the subscript.
first one is the mean, right?
Expected value, yes, the mean. The expected value. I think all of you know the expected value, is it? The mean, the expected value of the distribution. These three you can write as epsilon I following a normal distribution with mean 0 and variance sigma square notationally, combining the three of them. Now, on a side note, let's go back to some basics of statistics. If you have a variable x and you add a constant to it, the mean of x plus a constant will be what? Mean of x plus the constant. True? If I have a constant and I multiply it with the variable, The mean of A times X will be what? Not A square. A times expected value of X. That is for the variance.
Can you repeat the first one?
The first one is that if I have a variable X and its mean is 7, I have a variable X and its mean is 7. In each of the values of X, if I add 2 and try to find the mean of X plus 2, the mean of X plus 2 will be 7 plus 2. To be more exact, let us say I took major 1 of this class and the average came out to be 72. Okay, the mean of the class came out to be 72. Let's say I denote the score of each student by X. Score of each student is denoted by X and X is a variable. Okay, when I took the average of X, it came out to be 72. You understand up to this point? What I do is I give a bonus to every student, 5 points. Right? I give a bonus to every student, 5 points. And my new variable is Y, which is new score, which is old score plus 5. So what will be the mean of the new variable? Old mean plus 5. This is what we are doing here, expected value of X plus A. Similarly, if I say that I will not give 5 points to everyone, I will multiply the score of every student by 1.1, a 10% increment. It will be the second property of the mean. Yes.
Shouldn't we add assumption states that each pair of observation should be independent?
Yes. Yes, we will add that. It is there. It is there, but when I use it, I will mention it. At this moment, I'm not using it. Then there are a couple of properties of variance. What is variance of X plus A? If I have a class and the scores of the class is denoted by X and the variance of X is, let us say, 10. I give bonus, 5 points bonus to everyone. Will there be any effect on variance? The spread of the scores will be same. The variance of the scores will be same, no change. So variance of X plus A is simply variance of X as long as A is constant. As long as A is constant, it's simply variance of X. But if I multiply by a constant, what will happen to the variance? The constant will come out being squared. A squared times variance of X. If you have any confusion, go back and take a data of 10 values. 10 values, call it X. Then define a new variable Y, which is X plus 5. Find the mean of this new variable, find the variance of this new variable, and you will see that the mean of this new variable is actually the mean of old variable plus 5. And the variance of new variable will be nothing but the same as the variance of old variable. Then instead of doing plus 5, multiply it by something, a constant, any constant. And you will see the multiplicative property of expectation and multiplicative property of variance. Having these properties of mean and variance in mind, here is the model. What I was saying here is that at each point I have the mean of the distribution in the blue dot. So let me theoretically find what this mean is. If I apply the expectation on both sides, this will happen. True? True? Now in this one, what am I saying? I'm saying that this is a fixed quantity, a constant. This is a fixed quantity, a constant. And this quantity, I have fixed levels. All of this part is fixed. What is the variable part? Only epsilon. Use this property. Where is this property? The expected value of a variable plus a constant. Now here the variable is epsilon and the constant is beta naught plus beta 1 times x. So the constant will come out plus the expectation will only be applied on epsilon. True? Again, x.
Yeah.
We are assuming the x is to be fixed. Fixed means constant. Or if you're still confused, let me write this one. For a fixed value of x. This is the expected value of y for a fixed value of x. Yes.
Y is also not random.
Y is random because of epsilon. What is the expected value of epsilon? So at each point, the mean of y is nothing but beta naught plus beta 1 x. This point. Which means if this line is beta naught plus beta 1 xi, the mean of y when x is x1, you just plug x1 inside and you will get the mean of y for this subpopulation. Plug x2 into the line and you will get the mean. Plug x3 into the line and you will get the mean, and so on. This means we are after this line. We are looking for the line that is joining. The same thing I said as a statement, now I'm saying it mathematically. We are looking for a line joining those dots, this red line. We're looking for a line of expected value of y's when x is fixed. This is the line we're looking for. And to estimate this line, we need this and we need this. Now, what is the criteria I'm going to set? Now, let's say I take a sample. From this population. So in the sample, I will not have all the values of y when x is x1, maybe 1 or 2 values maximum. Now the sample will look like something this. Let's say this is x1, x2, x3, all the way up to xn. Maybe there is only one value of y when x is x1 in my sample. One value here, maybe 1 and 2 values here. Maybe just a 1 value here, and so on. 1, 2, and 3, and maybe there is 1 value here. One more here. Let us say this is the sample I got. Okay, now here in this sample, I'm going to fit 2 lines in front of you and tell me which one is better. There is one line here and there is one line here. Let me change the color. One line here. Now for both these lines, apparently it seems that the expected value of errors is close to 0. I tried to make the line such that half of the points are above the line, almost, and almost half of the points are below the line for both lines. Now tell me, which line do you think is better representative of the points?
I think the black line, because it covers more points.
The black line. Why do you think the black line is more representative of the points?
Because it covers more exact points, 4 points on the line.
It covers more exact points, okay?
Minimize the variation.
It minimizes the variation of what? The errors. Okay.
The arrows itself and the black line are less than the blue.
Yes.
The arrow for each point.
The error, yes. I'll give the specific name to what you are saying. Yes.
The distance between the black
The
line
distance, the magnitude of the errors, the magnitude of the individual errors is smaller for the which black line? Yes.
the slope for the black.
The slope for the black line is what? Smaller. So if you think that the smaller slope is better, I can give you a line with even smaller slope. Is this better? No, the slope should not be the criteria. Yes. Minimize the absolute error even more exact. Yes. Anyone else? The sum of the absolute errors. Okay, even more close. Yes.
The mean squared error.
The mean squared error. He said mean absolute error. You said mean squared error. What is the difference? Sum of squares of error. Why not absolute? Why squares? He said absolute. You said squared. Well, what's the difference? Let us continue in this direction. So the line we are trying to look for is the line such that the distance, the magnitude, the absolute difference between the line and the point is minimized for each point. Now, if I say that I want to minimize this quantity, summation of epsilons, or because I'm talking about sample, I will say summation of errors, EIs as the estimates of actual errors. Now, if I try to minimize this quantity, what's the problem? The problem is some of the errors come positive, some of them come negative, and the sum becomes 0, and it doesn't tell you the real picture. In all the 3 lines that you see, the sum of errors will be almost 0. So all the 3 lines are minimizing summation EI. This is not telling you the true picture. What's your name? What Fez suggested is to minimize this quantity. You put an absolute on EI so that if there are positive and negative errors, their effect doesn't cancel each other. All of them become positive. He suggested to minimize this quantity. And then somebody suggested the square of this quantity, not the absolute. Some of you think that they are same criteria. There is no difference between the two of them. Minimizing the absolute of the sum of absolute or minimizing the sum of squares is the same thing. Is it the same thing? No. Again? No, I'm not talking about beta 1. I'm talking about the difference between the line and the point.
There is a difference between them. The beta 1 with the
No. Wait. I'll start with the black color, with the black line. The E1 is this, E2 is this, E3 is this, E4 is this, E5 is almost 0, E6 is the difference between this point and this line, and so on. There are values of E, the difference between point and the line, and then I go red. Where are the points and the line? Here, E1 is this, E2 is this, E3 is this, E4 is this, E5, E6, E7. So the difference, the vertical distance between the line and the point is E. It's the error.
I was going to say that assume that all errors are between 0 and 1. Okay. If we take the absolute, it would give us a better indication, because if we took the square, it to be less than the absolute. So
All errors we cannot assume it. We cannot force them to be between 0 and 1.
if we assumed,
We cannot. Some of the errors for line will be big, some of them will be small, some of them will be negative, some of them will be positive.
just an
Yes.
assumption.
So wouldn't that affect the precision of our?
No. Forget about the precision. You can go as many decimals as you want. Excel can give you infinite many decimal points.
With square, it's differentiable, but absolute is not.
Next level. We'll talk about this. We always run away from the calculus. Yes.
The square is more sensitive to outliers.
The square is more sensitive to outliers. The objective here is not the outliers.
Minimized error.
It's not the outliers. At this moment, it's not about
Both
the
of them
outliers.
have the same goal, which is to minimize the
Yeah, both of them, they have the same goal. Basically, mathematically, if you talk mathematically, if you are looking for values of beta naught hat and beta 1 hat, the values of beta naught hat and beta 1 hat that will minimize this quantity will be the same as which minimize this quantity. Exactly same. There is no difference. The ones that will minimize the absolute of errors, the same will minimize the squares of errors, because the objective of doing absolute is what? To get rid of the sign. And same is the objective of taking square. You will get rid of the sign. You want to minimize what? The magnitude of error, right? Individually, you want to minimize the magnitude of errors. So the magnitude can be seen from the absolute. It can also be seen from the square. Why I was not minimizing this quantity? Because negatives and positives were canceling each other and I was not getting to the true picture. To get rid of that situation, you can either take the absolute or you can take the square. Now we come to this point. The point that you can use any of them mathematically to get to the formulas of beta naught hat and beta 1 hat, but I specifically prefer this one. Why? This is easier to differentiate. This is easier to differentiate, but even if you differentiate this one, you will get the same formulas of beta naught hat and beta 1 hat. Exactly the same formulas. So the objective function to estimate beta naught and beta 1, that is getting to the formulas of beta naught hat and beta 1 hat, the objective function is to minimize summation EI square. So a line that is minimizing summation EI square will be the best line, best representative line, which will be this red, black line. Out of infinite many choices, there will be only one line that is minimizing this quantity.
Is it the red line? How is it the red line?
How is it?
The red line. Why is it the red line that minimizes?
Because I tried my best to keep the red line closest to the points.
Which points? The errors?
Not the errors, the data points. The data points. Here I think this, and this. I tried my best to pass a line that is closest to most of the dots.
I'm talking about the black line, not the.
Yeah. Sorry, did I say red? No, black line, the black line. Sorry.
That's
Let us stop here. Stop here at the objective function. What we will do on Sunday is what? We will solve this equation and we will solve this equation, two equations. And in these two equations, we have two unknowns, beta naught and beta 1. And by solving these two equations, we will get to the estimates of beta naught and beta 1, and we will call those estimates what? We will give them notation beta naught hat and beta 1 hat. And those formulas will be the estimated quantities using least square method, least square. Why am I calling it least square? Because it is minimizing the squares of errors.
So you said at the beginning that there are many methods, but you're going to use
The least square, yes.
Why we are using that specific?
It's easier.
So it's not the most precise of any.
It's the one that is more precise. It gives the same formulas as that one. The most precise is the maximum likelihood estimation. So this one gives you the same formula as MLE's, maximum likelihood estimation. Now that you brought it, now we'll discuss MLE's.
That's for sure.
Okay, any questions at this point? Again, let us repeat the story. In statistical terms, we have an unknown regression line. Forget about this. We are after this line. Forget about the points now. We're talking about line. This is the line. I'm after this line. I want to estimate this line. And by estimating this line, I mean estimating these two quantities. Estimating these two quantities, right? To estimate these two quantities, number one, we make a number of assumptions. Chapter 4, we'll talk about these assumptions, whether they are true, not true. If not true, what to do, we'll talk about this. Chapter 4 is completely about the assumptions. We made a number of assumptions to estimate we made a number of assumptions. After making all the assumptions, now we have some methods to get to the estimated line. There are many methods in theory. We chose which one? Later in chapter 6, we will have another least square method, but it will be a more generalized least square method, which will be slightly modified and different one from the one we are using here. That is why I'm not calling this one as simply least square. I'm calling it an ordinary least square to differentiate in name from the modified one that we will discuss later. So you will see in books, this is called OLS method, ordinary least square. Using the ordinary least square method, we need an objective function. What is the objective function that we defined? To minimize summation EI square. This is the objective function. To achieve this, to minimize this objective function. In this objective function, basically on Sunday when I write the equation, you will see in the equation, the function, there will be two unknowns. There will be beta naught and there will be beta 1. So when you want to minimize an equation with a number of unknowns, what do? You differentiate with respect to every unknown and put it equal to 0. First derivative rule. When you do that, you hope for the solution. If you don't get it, you do what? You use the second derivative rule, which we will not go to. Luckily, we'll get the solution by first derivative rule. So what we are going to do is we're going to differentiate this function with respect to first unknown, with respect to second unknown, plug it equal to 0. And after solving the equations, we will get to this, and we will get to this. And finally, we will write this. End of story. This, we will say, is an estimate of the actual red line, which we are hoping that this estimated line is close to the actual line. So you see, everything is between this. This, I think, if I'm not wrong, this covers the first 5 chapters of your course. This one slide covers almost 5 chapters of your course. Now, in all the 5 chapters, we'll be digging deep with respect to more theory and more derivation. Other than that, there is nothing new in the first 5 chapters. At this point, if you have any questions, you can ask. If you don't have a question, you can leave. Those who came after the attendance, come to me.
The beta one, can we find this by slope equation? I mean, y minus y2.
When we do find it, we will get to know that it's the same slope equation. When I do derive the formula for beta 1 hat, you will get to know it's nothing but the slope equation.
I will get the slope, the beta one defined with this or not.
You will get the slope.
But the slope for the 1 point, right?
No. Which slope you're talking about? Here I have, where is here? I have many points. What about the line?
Okay.
Now, which slope you're talking about? Which 2 points? There are these 2 points. There are these 2 points. There are these 2 points. Which slope you want?
Okay, this equation will work like that.
Yeah. I want the slope of this line.
Okay.
Not the individual joining lines of 2 points. There is also one method that you are talking about. That one method is what? Make all the possible pairs of the points, find the individual slopes for each 2 points, and take the average of all those slopes.
Okay.
This is also one method. We'll not go into that, but this is also another method. It is longer than this one, but yes, it is a very good method. I repeat, how many possible pairs can you make? This with this, 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 this with this. There will be many pairs. Yes. Find the slopes, all the slopes for each pair of points, and then take the average of all those slopes.